is going to tell us how to pilot a spacecraft.
Sure. Thank you. And when we do an orbital launch, I'm sure that you will be able to photograph that one as well. A lot to look forward to.
Well, the SpaceX one was the first one I ever photographed.
Really?
Yeah.
That's quite impressive.
They talked about like, well, I hope I'm either going to get something or I'm going to get nothing. So where's it going to go?
Well, good evening, everyone. My name is Max Fagan. I am the Aerospace Education Officer for the squadron. And tonight we're going to talk about a subject that is very near and dear to my heart, which is the application of pilot skills to flying spacecraft and how that is a changing skill set. As I'm sure you are aware, Civil Air Patrol has recently gotten our 7th astronaut, Dr. Cyan Proctor, who was on the Inspiration 4 flight early last year. So there is obviously a lot of overlap between conventional pilot skills and being an astronaut, but in subtle ways there are differences that are important for us to keep in mind. I'm also going to cover a little bit of the intro to the subject of astrodynamics, which is the application of applied physics to calculating spacecraft trajectories, which are fundamentally different from the way we think about aircraft trajectories. The math is different, the terminology is different, though I hope you'll notice some common, some overlap and some common terminology. It's a very interesting discipline because, with the possible exception of propulsion, astrodynamics is really the only branch of aerospace engineering where there isn't really an analog to the other engineering branches. If you are a software engineer, doing aerospace software is pretty similar to doing software in another engineering discipline. You're just doing it to a higher quality assurance standard. You're doing structural engineering or vibroacoustic engineering. It's very similar in aerospace as it is in other disciplines, but astrodynamics is its own beast. It's very different. The dynamics of an orbit are completely different from the dynamics of a car or an aircraft or something that we're more familiar with in our everyday study. And most of the critical limits on space missions, payloads, thermal, communications, duration, consumables, most of those things can be tied back to an astrodynamics limit. So it's a very important starting place when you're doing the spacecraft design. And unfortunately, most of the terminology that we're going to be covering tonight was invented by the ancient Greeks, with most of the math invented in the 17th century. So we're kind of stuck with some anachronisms and some modern terms, which kind of make it a very weird thing to talk about. So it's been a very exciting year in spaceflight this year. Every year for the past decade or so has been an exciting one for human spaceflight. There were two crewed SpaceX visits to the International Space Station, the Axiom-1 private astronaut mission and the NASA Crew 4. And just this week, as I'm sure you're aware, the Orion spacecraft, the Artemis 1 mission, came back from its translunar flight around the moon, spending about 25 days in orbit. No pilot on board, but accommodations for 4 astronauts, including this mannequin right here, meant to demonstrate the viability of the vehicle. For
Didn't they have 2 other mannequins?
say again.
Didn't they have 2 other mannequins like in the backseat?
I believe they did. I believe that. So I think they had a anatomical female and an anatomical male to study radiation dosage throughout the body.
Those giant windows.
These are windows right here and right here, as well as right here and right here. They have different functions for docking and ascent. Yeah, that's what those 4 are right there. So the internal structure and how we interface a pilot with a spacecraft has changed a lot in the last decade. Just here you can spot the difference. Here on the left, this is the Apollo and Russian Soyuz. This is kind of what you see in an Apollo and the Russian Soyuz. Analog, there's one button, one function. There's no digital displays. Contrast that with what you're seeing in modern displays. Up here, this is the SpaceX Crew Dragon, and down here is the Orion capsule. There's a combination of physical inputs as well as multifunction displays, which can be a lot more information rich than could in the past. But it also means a lot more of the functionality is automated, and a lot more of it has been put between another layer of abstraction between the human and the vehicle that they are flying. So what does it even really mean to fly a spacecraft anymore in this new world? Because it still requires an immense amount of skill, but it's not the kind of seat-of-the-pants airmanship that we're used to thinking about when we're flying a Cessna 182. The forces that operate on a spacecraft do have some analogs to the forces that we're familiar with thinking about on an aircraft. 4 forces of flight, only 2 of them are ever really present on a spacecraft that's in orbital motion, thrust and gravity. There are other forces, solar radiation pressure, for example, the light pressure from the sun, and aerodynamic drag is still present even in orbit, but it's measured on the scale of micropascals instead of kilopascals. So the actual dynamic pressure from atmospheric drag in space we tend to ignore. Same thing with light pressure, leaving us with really only these 2 important forces, thrust and gravity. And most spacecraft, their thrusters are off 99.9% of the time, unlike a conventional aircraft. So you can model it as the same force as you would for an aircraft with no air and no engine. That's a considerably simpler dynamic model. However, the fact that we're not working in a conventional Cartesian space, where it's just forward, backward, left, right, up, down, complicates things. Spacecraft are moving so rapidly that you can't ignore the curvature of the Earth, and talking about up and down is a lot more subtle than it is when we're talking about an aircraft, and that leads to different terminology and different ways that we have to handle the dynamics here. So let's go through the math roughly. This is the only math in this presentation, I promise. The law of gravity that we're all familiar with from high school states just that gravity is inversely proportional to the square of the distance, the square of the separation between two bodies, so spacecraft and the planet that it is orbiting. Force of gravity is in direct proportion to the product of the masses of these 2 objects and inversely proportional to the square of the distance between them. That's the only force that's operating on a spacecraft substantially for most of the time that it's really flying. So the force of gravity, Newton's gravitational constant times the product of the masses over the square of the radius. Now, there's a couple of important things that can be derived just from this simple law alone. The first one is that the definition of down depends on your physical location. It's always central. The force of gravity is always towards the center of the planet. It's independent of the size of both objects. The mass is important, but if the Earth had the same mass and was just a larger planet without getting more massive, the orbital motion of a spacecraft around the Earth would still be exactly the same. It also doesn't matter what shape your spacecraft is. It only matters what is the mass of the spacecraft. So that's a good simplification that helps simplify a lot of our discussion here. And of equal importance is the fact that the force of gravity, is what we call conservative, meaning that it's path independent. If you remember your vector calculus, it means we can write gravitational force as the vector gradient of some scalar potential, if you remember your vector calculus. But the takeaway from that is closed paths exist. Any object that is moving only under the force of a conservative force, where you can write it as the vector gradient of the scalar potential, must have closed paths of motion, which in this case we already know because we know orbits exist. And this is true of any inverse square force. So it's convenient that the universe came down this way, or else there'd be no way to do closed path motions around planets, which we find so useful. So these closed paths, orbits, can only take on a certain number of shapes, and we capitalize on the uses of these shapes for different applications depending on the spacecraft. So it was known early in the Renaissance era that these closed paths, if you go through the mathematical derivation using the law of gravity and ask what are these closed paths, it turns out that they can only take the form of what we call conic sections. Conic section is what you get if you take a cone, a three-dimensional cone, and you cut with a plane. If the plane is parallel to the cone, like this one, cutting straight through the cone, then the cross-sectional surface that you get when you look at what the intersection between the plane and the cone is a circular orbit. But there's no reason you have to cut the cone in that direction. You can cut it angular, you can cut it sharper, you can cut it vertical. All of those shapes, any of those shapes, are a valid orbit operating under this assumption. So orbits can't take any shape, they can only take a limited number of shapes, and each of those orbits has different applications depending on the type of spacecraft that we are flying. So the 5 classical kinds that we talk about are the degenerates, the point in the line, circle, ellipse, parabola, and hyperbola. Those are the categories of orbits that we can typically get. The 2 degenerate cases here are kind of uninteresting cases. If you cut the cone directly at its apex, so the intersection between the cone and the plane is just a point, then this itself is technically a valid orbit. What does this represent? Well, this represents a satellite hovering in the middle of the Earth. Newton's law doesn't know anything about the surface of the Earth. It only cares about the masses. And as far as Newton's law, as far as the law of gravity is concerned, a valid orbit is just hovering right in the center of the Earth. But you can also just be falling straight down towards the planet. Those are what we call the degenerate cases, a point and a line. But they're technically valid orbits. There's nothing mathematically invalid about that. There's just not a lot you can do that's interesting with them. The more interesting ones are what we call the periodic cases. So there's the circular orbit, where you cross through the cone directly parallel to the base of the cone, and the ellipse, where you take a cut at an angle. These are going to cover all of the orbits that you're ever going to encounter in a satellite operations context, and in most crew spacecraft contexts. Even the Orion orbit that was transiting between the Earth and the Moon was well approximated by an ellipse for a majority of its flight. The distances were quite large. If this was the Earth to scale, this is about a 1/37 million scale model of the Earth. Whereabouts would the Moon be on this scale? Right.
The terminal building.
Terminal building?
Yeah.
Any other guesses? It'd actually be right about there. See? Turn around. To scale, that's also about a 1/37 million scale model of the Moon. That's about the actual scale between the Earth and the Moon. Yeah, but still, you can see that's quite a fair distance compared to the conventional distances of crew spacecraft. All crew spacecraft operations in low Earth orbit, the Dragon, the International Space Station, the Space Shuttle, none of them ever went more than a finger's distance away from the Earth. Hundreds to 1,000 kilometers at most. It's not very far on this scale. So the Orion really did make quite a fair distance getting to the Moon. But even in that situation, for most of the flight, its orbit was well approximated as an ellipse. That approximation breaks down when the gravity of the Moon and the gravity of the Earth are both significant forces, because you can see this derivation only applies to a single central force. It's not valid when there's two large forces of gravity operating on the vehicle. But even on the way out, until it was maybe 50 or 60,000 kilometers away from the Moon, it was still moving on a path that was very well approximated as an ellipse. These two cases, the parabola and the hyperbola, we call open orbits. And really the only times when you're going to encounter these types of orbits are if you are departing the Earth-Moon system, so if you're flying interplanetary, or if we're not talking about a crew spacecraft, or if we're not talking about a spacecraft, we're talking about something like a comet. Comet orbits are well approximated by parabolas, and if it's an interstellar comet, which we've seen a couple of, just a couple of years ago we had a couple instances of comets / asteroids, we don't really know what to categorize them as, that were passing through our solar system from interstellar space. And those paths are well approximated by hyperbolas. But this doesn't generally apply to crew spacecraft unless you're visiting interplanetary space. So all 5 of those orbit categories, they all operate under the same laws of physics. They're all described by the same equations of motion. That's true of us too here on the surface of the Earth. This object, if you do that, it's moving on a ballistic trajectory. It's suborbital. It's going to intersect the ground relatively soon, so it wouldn't be convenient to describe this as an orbit. But technically speaking, you could model this as a parabolic orbit centered with one foci on the center of the Earth. It's the same for a human being that's jumping. It's the same as if you are base jumping off a cliff. All 3 of these objects are in orbit. It's just 2 of them are suborbital. They're going to strike the Earth relatively soon, so we don't usually talk about that as being in orbit. But as I'm sure you all are all aware, if you're in an aircraft and you dive down, you go into free fall for a period of time, you are going to feel the exact same zero gravity as an astronaut on orbit, and for exactly the same reason. Free fall is weightlessness in exactly the same way that that astronauts in the ISS are. It's all the exact same reason. It's just much easier to sustain weightlessness when you're going around the Earth than when you're in an airplane diving for the Earth at 300 knots. But it's exactly the same phenomena of weightlessness. That's why astronauts are weightless, is because they are in free fall. Exact same reason as when we're diving an aircraft. So the intention of the intention of all this is really just to get across the point that it's the same laws of physics that govern objects in free flight here on the ground as it is the objects in space. It's just objects on the ground. You can't usually ignore air drag in objects in space. You can. It's also important to remember that space itself, this astronaut right here, is not terribly far away. Space itself is closer to us than South Dakota. We're closer to space right now than we are to Canada. Space is not very far away. The official boundary of space is only 100 kilometers up. You know, there are particularly powerful rocket-powered aircraft that can go on a ballistic hop to that altitude. It's not terribly far away. The majority of propellant that is in a launch vehicle, like you could take a look at the SpaceX Falcon 9 right here, the majority of propellant that is in a launch vehicle like this is not about getting high and getting to space. It's about going fast enough to achieve the critical velocity where you can enter free fall around the Earth, where you're going to miss the Earth when you are as the Earth curves away from you. If we make some simplifying assumptions about this, you know, then the optimal way to accomplish this is what we call a gravity turn. So this is a time-lapse photo taken of a launch trajectory out of Cape, and you can see the vehicle starts its ascent nearly vertical, but then very rapidly tips over into the horizontal. And the reason for that is because, again, it does not need to get very high. It needs to go fast, 7 kilometers per second, about 15,000 miles per hour, in order to achieve an orbital state. Minor note to make us kind of proud of our humanity from this. There are a lot of places in the solar system where intelligent life could have evolved, but because of Earth's atmosphere and mass, we humans, we have evolved in pretty much the hardest place in the solar system to launch a space program from, where life could have evolved. You know, it's conceivable that we could have life evolving on a much harder place like, say, Jupiter or the Sun. But if we assume that intelligent life like us has to evolve on a rocky planet with a relatively cool surface and liquid water, we evolved in the hardest spot in the solar system to launch a space program from. So whenever you see a rocket launch successfully to orbit, you can take some serious pride in your humanity for that. We are doing this. We are doing this from the hardest place in the solar system where it could happen. If we ever encounter intelligent spacefaring aliens, we will probably have a significant boasting point on this fact, because we have evolved from a. You think your space program was hard to get out of the ground? Wait until you see our planet. Yeah, if we had evolved on a place like Mars or Titan or Enceladus, getting to orbit would be 5 to 10 times easier or cheaper. You know, we could have gone to the moon with the size of rockets that we usually fly, that we first took humans up into space on in the Mercury and Gemini days. So be proud of your humanity for that, because the universe has stacked the deck against us pretty difficultly. All right, so how does our pilot intuition kind of wrap to this? So we don't usually teach aviation skills in terms of coordinates, but it's important to remember that all of these instruments, on a mathematical basis, all of these instruments are about conveying to us really 6 numbers. We need to know our position, which is a 3-coordinate information, and we need to know our velocity, which is a 3-state vector. We don't think about it that way because we're not computers. We find it much more easy to think about our state vector, as we would say, the combination of these 3 numbers. We find much more convenient ways to talk about it. You know, we don't care about our distance from the center of the Earth. We care about our MSL altitude. We don't care about our latitude and longitude. We care about how far away are we from the airport, how far east and how far north. But fundamentally, what really matters as a pilot is we have to have an understanding of 6 numbers that uniquely define our state vector of the aircraft. And we're free to pick which of those 6 numbers are most convenient for us at any one moment. But it really is about getting those six numbers which define our state vector. And the same thing applies to spacecraft. Spacecraft require an understanding of 6 numbers to define the state vector. But we don't use the same 6 numbers that we're used to using as pilots, because these numbers turn out to not be very useful. The way we usually do it is by talking about what we call orbital elements. So if you think about the aviation analog of altitude, latitude, longitude, vertical speed, heading, and airspeed, those might be 6 numbers that we care about in order to specify our state. The 6 elements, the 6 numbers that we care about as astrodynamicists, those 6 numbers would not be useful. First reason being is because all 6 of those numbers would be constantly changing. If we talk about our altitude as one of our 6 numbers and we're in an elliptical orbit, our altitude is going to be constantly changing. There's no analog to straight and level flight when you're in an elliptical orbit. If we talk about our heading, it makes sense to talk about heading for seconds to minutes in an aircraft, but if you ever fly transoceanic, you know if you start here in New York and you set a heading vector to due northeast, and then you just keep flying due northeast, you're going to take a curved path. If you wanted to fly from one point on Earth to the other, you can't fly a constant heading or a constant bearing. You're going to miss your target. Well, imagine if you're going around the Earth once every 90 minutes. Your heading angle is going to be constantly changing. It's the same problem with your latitude and longitude, constantly changing and in ways that are very unintuitive to understand. So as astrodynamicists, it would be really nice if we could pick 6 numbers where the majority of those numbers were constant, where they would only change if we intentionally changed something about the way our spacecraft was flying. And through a process of trial and error over a century or so, we have kind of come down to a combination of 6 numbers that are very convenient to work with, which we call the classical Keplerian orbit elements. And these 6 numbers are what we talk about in the same way that pilots talk about airspeed, altitude, and heading. You will hear astrodynamicists talk about these numbers. So let's talk a little bit about what these 6 numbers are, because they're important for getting a good intuition about how a spacecraft is flying. So the first 2 numbers here, A and E, are what we call the semi-major axis and the eccentricity. The semi-major axis you can think of as the equivalent of your altitude. The semi-major axis tells you how big is the orbit around the planet. A low-altitude circular orbit has a very small semi-major axis. A large orbit has a large semi-major axis. And what it is it's just half the distance from the center of the Earth to your orbit, if you're in a circular orbit. That's the semi-major axis. The eccentricity describes how oblate is the orbit, how elliptical is the orbit. So an orbit with 0 eccentricity is just a circle. An orbit with an eccentricity of 1 is a parabola. Anything between 1 and 0 is an ellipse, with 1 being the more elliptical side. Translunar orbits that go between Earth and the Moon tend to have eccentricities on the order of 0.9, 0.95 or so, whereas the low Earth orbits that are nearly circular will have eccentricities of 0.0001 or so. So these 2 orbits describe the size and the shape of the orbit. Semi-major axis, how big is the orbit? Eccentricity, how elliptical is the orbit? These 3 numbers, the inclination, the longitude of ascending nodes, and the argument of periapsis, are the Euler angles. They're the analog to pitch, roll, and yaw. But they're not describing this. They're not describing the attitude of the vehicle. They're describing the attitude of the orbit. So inclination describes how tilted is the orbit from the plane of the equator. An object that is orbiting the Earth in the plane of the equator, so like this, if my left hand is on the North Pole, this has an inclination of 0 degrees. If it's going around the Earth like this, that's an inclination of 90 degrees. So that's one of the Euler angles. The other 2 Euler angles, the longitude of ascending nodes and the argument of periapsis, tells you how is the orbit rotated in the other 2 directions. So those combination of 3 orbits gives you a specification of the orientation of your orbital plane in inertial space. So 2 elements for the size and shape, 3 elements for the orientation of the orbit. And then the final one, what we call the true anomaly, is the only element that changes with time for the most part. So the first 5 elements right here, because of the way we've picked them, these can be made analogous to what is your airspeed, your vertical speed, your heading, and your altitude if you're in straight and level flight. They're constant. Those 4 numbers are constant. And for an object in orbit around the Earth, not thrusting, not subjected to any perturbing forces, these first 5 elements are constant, and it's only this one that all the change has been packed into. So true anomaly refers to the angle between the spacecraft's current location and the most recent perigee being the point of closest approach. So that's constantly changing. An object in a elliptical orbit like this will have a true anomaly of 0 degrees here, 90 degrees, 180 degrees, 270, and 0. So an object in an elliptical orbit like this, its true anomaly will be constantly changing, but all other 5 elements will remain constant. Unlike if we were to use the 5 numbers like latitude and longitude. Latitude and longitude, high latitude, low latitude, they would be constantly changing. It'd be very difficult to talk about the state space of the spacecraft if we use those numbers. But with this combination of these 6 classic Keplerian elements, it becomes a lot easier to talk about what our spacecraft is doing at any one point. So yeah, so these are the classical Keplerian elements, and it's important to have a good sense for them in the same way as a pilot does with, we do for altitude, airspeed, heading, all of the conventional things that we're used to getting off of our instrument panel. A little bit of terminology. So we refer to the direction of motion as prograde and retrograde. So if a spacecraft is going about the planet in the same direction as the planet is rotating, so west to east in this case, we say it's a prograde orbit. If it's going around west to east, or sorry, east to west, that's a retrograde orbit. We define the point of closest approach as the periapsis, or sometimes we will change the last term, the last few letters of this to refer to the specific body. So periapsis and apoapsis, the closest and the furthest point. And we will refer to, if we're orbiting the Earth, for example, we'll sometimes call this the perigee and the apogee, G meaning Earth. The eccentricity refers to how eccentric the orbit is. And the terminology depending on the central planet. So perihelion and aphelion for the Sun, perigee and apogee for the Earth, aposelene and paraselene for the Moon, Selene being the lunar goddess, apoarian, para-Aryan for Mars, apogee, parajove for Jupiter, etc., etc. So this is useful in a mission planning context because you might have multiple objects that you visit in the course of your flight. So yeah. That's the basics of orbital terminology and orbital elements. Now it's important to talk about how do we change these orbital elements, because a mission profile where you're just stuck in one orbit all the time isn't terribly useful. It isn't terribly useful for a crew spacecraft. It's very useful if you're a GPS satellite, for example. The GPS satellites are in middle Earth orbit. They're like about this high or so, a few tens of thousands of kilometers. Or if you're in a geosynchronous orbit, a weather satellite, a geosync, something like 35,000 kilometers, like maybe this high, it's useful to be in one orbit all the time. But for a crew spacecraft, where you're going to be traveling from one destination to another, it's important to be able to change our orbit. So how do we do that? Well, we change orbital parameters by exchanging kinetic energy for the energy in our propellant system. Now, this exchange of energy is happening all the time in a conventional orbit, even when the engine is not firing. If you remember from high school physics, there's two conventional mechanical types of energy. There's potential energy and kinetic energy. Potential energy being the kind of energy that's associated with something that's high up and can be dropped. Kinetic energy associated with something that is moving rapidly. A conventional Keplerian elliptical orbit is a constant exchange between these two. So an object in an elliptical orbit at high altitude has a lot of potential energy, but not a lot of kinetic energy. It's moving slowly, and then as it swings around perigee, it speeds up, slows down, speeds up, and slows down. So low near perigee, it has a lot of kinetic energy, but not a lot of potential energy. High up in its elliptical orbit, it has a lot of potential energy, but not a lot of kinetic energy. And it's this constant exchange that we capitalize on when we change the orbital elements. So what if when we're swinging by perigee, we fire our engines, program? We're now adding energy to the system. We're converting energy from our propellant tanks into kinetic energy of the vehicle, which is going to change the orbit elements. And this is why you hear aerospace engineers typically talk about maneuvers and maneuvering budgets in terms of delta V. Delta V is a spacecraft's capability. How much capability does the spacecraft have to affect a change in velocity? Because by changing velocity, you're changing your energy, which means you're changing your orbital elements. So you'll hear engineers talk about delta V like it's something we can consume. You'll hear us talk about it in the same way as pilots would talk about gas budgets or fuel. It's the currency of exchange in astrodynamics is usually spoken in terms of delta V. So an example of that maneuver might be, let's say we're in a high orbit and it's time to come back for entry, descent, and landing. The vehicle is coming in on a highly elliptical orbit. We pass by our perigee and we fire the retro rockets retrograde. That's going to reduce our velocity from a high velocity to a low velocity, the difference being the amount of delta V we affected. And the result is going to be moving from a highly elliptical orbit to a slightly less eccentric orbit. And then if we did it again, we could break into a circular orbit. If we did even more, we could break it to an orbit that intersected with the Earth's surface, which is what we want to do when we're trying to come back from orbit. So the easiest way to think about this is the way to change your elements is by changing your velocity. Fire your engines, change your energy, change your velocity, change your elements. Change your elements, change your orbit. So the exchange between delta V and how they affect our orbital elements is very important for mission planning. An example which I can show you here is the International Space Station. So I have here the conventional elements of the International Space Station. You can see though this isn't really very useful. This isn't really going to tell us anything because in 10 seconds all of these are going to be different. But if we convert them to the Keplerian elements of the ISS, they tell us a little bit more useful information. So for example, the ISS has a semi-major axis of 6,782 kilometers. Who knows what the radius of the Earth is, roughly? No? It's 6,370 kilometers. 6,370 kilometers. So if the Earth's radius is 6,370 kilometers, we know the ISS here is about 400 and something kilometers high. So that tells us something useful. This wouldn't really tell us that because you'd have to do the Pythagorean theorem with these three components to figure out the orbital radius of the space station. The eccentricity of the ISS, very, very small, tells us it's in a roughly circular orbit, which is good. The inclination, 51.6 degrees, is a historically picked number. So lower inclinations are easier to launch into because you can launch due east and capitalize on the rotation of the Earth. But the International Space Station is an international space station. It's right there in the name. It's not just assembled out of Cape Canaveral. There are components of the International Space Station that needed to be launched from Russia. And an orbit with a low inclination that always stays over the equator is never going to pass over Russia or the Soviet Union at the time when this planning was done. So it was necessary to increase the inclination of the ISS so elements that were launched from the Soviet Union could reach it. Otherwise, there'd be no way for the Russian elements to get up there. And inclination changes are incredibly difficult afterwards. They're as expensive as launches. So once the ISS was in this 51.6 degree orbit, there's really no reason to move it off of that. It would take as much delta V, as much rocket power as it did to launch all of these elements in the first place. So the orbital inclination of the ISS tells us something about how high latitude, north and south, it will go. You can see it goes to a high enough latitude that it crosses over a significant portion of the Soviet Union, which is how they launched to it out of Baikonur in Kazakhstan, which is right here. Radiation is another factor that's impacted by our selection of orbital elements. The Earth has two significant radiation zones called the Van Allen radiation belts. One of them kind of at low inclination, low altitude, another one at a wider inclination band and a higher altitude. An orbit with a low inclination is going to spend a lot of time inside these belts, whereas higher inclinations will kind of get out of them for a significant period of time. Of course, if you're at a very low altitude, you're never touching the belts. But if we go up much above 1,000 kilometers or so, that's a lethal dose for astronauts in a matter of weeks to months. So it'd be very unhealthy for astronauts to hang out inside the Van Allen radiation belts for an extended period of time. You could fly through them just fine, like the Apollo astronauts, for example, only spent a matter of hours inside the Van Allen belts. But you wouldn't want to set up a space station at a high enough altitude that it impacts the Van Allen radiation belts. It matters for computers, too. This is a kind of fun map. This is a map of all of the locations that a flight computer on board a spacecraft suffered a single bit upset. So this is a kind of error that computers will encounter when they're bombarded with intense radiation. And you can see that if you put a dot everywhere where there is a single bit upset, we get this cluster of them over South America. We call this the South Atlantic anomaly. And it is a known hole, it is a known region in the Van Allen belts where the radiation dips down to a much lower altitude. And anytime a spacecraft is passing through the Van Allen belts, it can take a radiation exposure 4 to 5 times higher than it would the rest of its orbit. For operations on the ISS, we don't schedule EVAs when the ISS is going to be passing through here in order to keep the astronauts' dose low. It's important not to schedule really critical operations when you're going to be passing through the South Atlantic anomaly. Lots of important changes need to be made in order to avoid that radiation dose. And by proper selection of orbital elements, you can minimize the amount of time that you're going to spend inside the South Atlantic.
Is there an impact on aviation as well by that?
I want to say yes, but I'm not aware of any data that indicates it would be the case. But yes, the radiation dosage would be marginally higher off the coast of South America than it would elsewhere. I just don't know if it's high enough to impact aviation operations because we have 150 kilometers of atmosphere between us, which stops the majority of space radiation, regardless of the Van Allen radiation belts.
There are ozone limitations, which I don't know if that's related to the Van Allen belt.
That's separate. Yeah, the ozone limitations are entirely due to our atmosphere.
They're limited to time, altitude, and latitude. As in time of the year, latitude and altitude.
Altitude selection is important from a propulsive perspective because it matters how much propellant is going to be allocated to reboosting the vehicle. So this is the altitude history of the International Space Station over a period of about 2 years. Now you notice the vertical scale is highly exaggerated here. It's a difference of 400 kilometers to 406 kilometers. So the surface of the Earth, way down, way off scale here. But you can still see that over a period of time, over about 2 months, the space station loses 5 kilometers in altitude due to atmospheric drag. And then every so often it needs to burn its engines again to reboost back up to a higher altitude. That's what these stair-step functions are right here. This is the ISS firing its thrusters for a few minutes to gain some altitude back. This falls off though with higher altitudes. Every 100 kilometers of extra altitude or so is about a factor of 5 reduction in atmospheric drag. So if you don't want to expend propellant keeping your spacecraft aloft, it's good to send them higher up. Yes?
Is the propellant replenished?
It is not. No. We have studied very out there concepts of spacecraft that can refuel themselves, or at least refuel their oxygen by collecting it from the ionosphere. But no one has yet found a way to make it practical or worth the time.
So the lifespan of the orbit is a function of the propellant that you launch with.
Yep, in most practical applications, that's the case. Much above 600 kilometers or so, the drag is so low that you can have lifetime of decades to centuries without reboosting. But down here where the ISS is, at about 400 kilometers, if the ISS stopped reboosting, it would deorbit in about 3 to 6 years.
I was wondering about the phenomena of you've got the 2 significant drops in that late 2015, and they let it go for a couple of months before they reboosted. And so it does look like there's this pattern now of we're going to reboost more frequently, but still, if you get to like February, March of 2016, and then they wait a while, but it doesn't lose as much, what explains that?
So, the altitude at which we reboost is driven by a lot of operational considerations. One of the most common ones is when is the Soyuz going to be coming up to visit, the Russian Soyuz. The Soyuz likes us to be at low altitude. It's not a very it's not a very high Delta V vehicle. It's much easier to do fast rendezvous with the Soyuz when the ISS is lower. So if we know that there are going to be multiple visiting vehicles coming in pretty soon, we'll just let the ISS get a little bit lower and make it easy for the visiting vehicles. But it also matters, we want these reboost periods, they disrupt the microgravity on the space station. You know, a key selling point of the International Space Station is we can offer researchers extended months with minimal interruption to their microgravity environment. But when we turn this on, you know, things start falling to the backside of the spacecraft. It's a very small acceleration, but you can still feel it, you can sense it. So that's going to be a disruption to all of the things on the ISS that require zero gravity. We don't want, the best time to do this, the best time to do these reboosts is actually when a visiting vehicle is on station and the visiting vehicle can push the ISS. That doesn't require tapping into the ISS's propellant budget. So when these reboosts happen is a combination of multiple operation factors with dozens of team leads getting together and deciding when the best and least disruptive times for them are. But that's why they're not regular recurring periods.
That vehicle is also
Now,
a culprit too, right? Because that vehicle is adding mass.
Oh.
right?
It is, but it's still much easier for the vehicle to do the reboosting because it doesn't require transferring any propellant onto the ISS. If the visiting vehicle can do the reboost, we always let the visiting vehicle do the reboost. Because the alternative is the vehicle has to dock with the ISS, we have to unload propellant, take it across the hatch, plug it into the ISS's propellant tanks, and then have the ISS do the reboot. And that's a lot more effort than just letting the vehicle do the pushing. But yes, a visiting vehicle can change the space station's mass by 2 or 3%, and it's something we need to calculate.
So you talked about the disruption caused by the thrust. That was actually a project I worked on at NASA, was
Oh, really?
how to control experiment in space. And we can talk about that another time.
I really would like to hear about
yeah,
that.
we used an active control system and electromagnets to keep everything stable.
Fun.
Basically.
Yeah, I'd love to hear about that.
Anyway, keep going.
Now, the second part of your question is, why is the ISS coming down so much quicker here than it is here? You can see this is about, call it 5 kilometers every 2 months, whereas this is more like 5 kilometers every 4 to 6 months or so.
The atmosphere changes.
The atmosphere changes. This was 2015, 2016. 2016, the sun was on the downswing of its solar cycle. The sun goes through 11-year solar cycles, and when the sun is at low activity, during periods of low activity, the atmosphere, the thermosphere, and the ionosphere actually cools down, shrinks, and causes less drag. And when the sun is active, it bombards the upper atmosphere with radiation, with thermal radiation. The upper atmosphere heats up, swells up, and the atmosphere starts to drag more. So we actually have to. It is a huge variable. It can change. The amount of drag on a spacecraft at a given altitude can vary by an order of magnitude, depending on whether it's solar minimum or solar maximum. Right now, we are entering we just came out of a pretty deep solar minimum, and it's starting to ramp up now. It'll peak sometime in the mid-2020s and then start to diminish around 2030 or so, and then start to ramp up in 2031 or 32. But yes, this is a order of magnitude effect on how hard it is to keep a satellite out there, depending on what the solar cycle is doing. Communications is another thing that is impacted by our orbit selection. Every one of these circles right here, it is a circle in a globe projection, but it's going to look slightly warped elliptical in a Mercator projection here. Every one of these is a ground station for the International Space Station. These big blue circles right here are regions that are covered by TDRS, by satellites in GEO. When we're passing through these regions, the ISS is capable of more communication than it otherwise would be, so our orbit selection matters there. If we have a commercial satellite that needs to downlink a lot of data, when is it going to be passing over these comm sites? How long is it going to be in sight? How high above it is going to be? How high above the horizon is it going to be? All of these things are affected by orbit selection. Thermal and power is impacted by our orbit selection. Right now, actually, just as of yesterday, the ISS entered what's called a high beta period, where the ISS actually does not experience any sunsets. It'll be that way for about another 3 or 4 days. There are going to be no sunsets on the ISS because its orbit has lined up very closely here with the terminator, with the day-night terminator on the Earth. And as a result, the ISS is going to be going through periods of full sunlight for several days. This is a thermal problem. The ISS can't operate normally during this time, or else it'll overheat. It's unusual for there to be visiting vehicle operations during this time. The space station sometimes has to yaw to a completely different attitude and then kind of fly sideways to avoid overheating. It's very annoying, but it's an artifact of the fact that we needed to be at a high enough inclination to access Baikonur in Kazakhstan. We can fix this by going to a lower altitude, but lower altitude, more drag. Got to launch more visiting vehicles to keep the station reboosted. Of course, sometimes we can capitalize on this. There are sometimes spacecraft that you want to always be in the sun. If you have something that needs a lot of power, needs permanent sunlight, if you have a solar telescope, it's convenient to be able to locate it in an orbit that always has sun. And you can do that. Those are called sun-synchronous orbits. So like every branch of engineering, everything I've told you here is shorthand for a lot of math. The way this is actually done is computationally with custom software. If you've ever heard of STK or Free Flyer or anything like that, these are basically flight planners for satellites. They do the same thing that ForeFlight does, but for orbit design. And they'll answer all of these questions about communication access, illumination conditions, perturbations due to bodies like the moon and the sun, shoves all of that math under the hood in a way that's very convenient to do, and was something that people in the 60s and 70s who sent us to the moon would have very much appreciated having. But it's still important to have a good intuitive sense for this when you're doing trajectory design, so you know what knobs to turn and what buttons to press. So yeah, it's a fascinating field of study, and there's a lot of great resources online if you want to learn more about astrodynamics, because it's a fun perspective changer when you start thinking, especially when you have a mind for airplanes and you start thinking in terms of spacecraft. Kind of extends your mind to the possibilities that are out there. Are there any questions?
I have two. One, I'd be fascinated to learn more about the discussions of how they came up with the 6 numbers.
Why
As
we
you said it took a while. There must have been a lot of back and forth.
Yep.
And is there just you can point to like a sort? No, it's just
Nope.
try and find it.
Nope. And if I was to point you to the source, I would be pointing you towards Kepler.
Yeah.
Towards Kepler and all of the astronomers whose legacy we are inheriting right here, because there are not just 6 orbital elements. There are many
Right.
combinations.
You
that
said
you can
but they
pick.
arrived at those.
We've kind of just come to these by trial and error, back and forth, and Darwinian evolution. The papers that use these were were the easiest ones to understand, easiest to educate our students with. Just how we came to it.
And then, do spacecraft still have it's added, what I would call it, an attitude indicator?
We do, yes, we do. Now, the way we talk about attitude can depend a lot on what kind of spacecraft you're talking about. So a lot of spacecraft, like the space shuttle, for example, fly like an aircraft. They need to have the conventional aircraft inputs, pitch, roll, yaw, etc. Not all spacecraft, though, for not all spacecraft is that a convenient way to think about. For example, a capsule like this. A capsule, when it takes off, it's flying like this, nose into the wind. When it's re-entering, though, it's basically flying backwards. So in many cases, thinking about conventional pitch, roll, yaw is less useful. It's more easy just to think about things in terms of flight path angle, angles of attack, and roll. But yes, most conventional spacecraft here. Let me even show you the one on Orion. Right there.
Yeah.
You can see it's a digital version of a gyro. Yes.
On a historical note, following up on Matthew's question there, at the Udvar-Hazy Center, they've got a big space section, and you can check out all the vehicles, or a lot of them anyway. At one time, they had a Mercury capsule, probably still have it. It's probably still there. But the first time I looked inside that thing, they got the hatch open. You can stick your head in there and look around. It had the exact same attitude gyro that my A4 had. We called it an AJB3 Alpha. I thought, seriously? These guys went in the friggin' outer space with the same attitude indicator I'm flying with?
Well, so this right here, if you're looking at the Soyuz cockpit, you might be inclined to look at this and say that's the attitude indicator. It's not. That's an actual physical globe that they use to select the landing site. So if the Soyuz needs to do a manual abort and you need to select which landing site, you can turn this globe. It's like a globe like the size of my moon globe back there. You turn it to put a crosshair physically over a 3-dimensional globe in order to select your landing site. So yeah, it is early space programs had a very hardware-intensive avionics setup. That's true for Mercury. That's true for Gemini. That's true for the Soyuz.
Max, when you do blue?
I work on Orbital Reef, our space station,
Specifically?
Astrodynamics and mission design.
Is it possible for humans to control these ships now,
Yes.
given the complex orbits and everything that we have?
It is possible. It's not necessarily safe because the propellant budgets are very narrow, and humans, as talented as we are, we're not as good at optimizing as a computer is. So for most of these situations, if you had a human fly it completely manually, it's likely we would exhaust our propellant budget. Doesn't mean that we've given up on humans controlling them. It just means we understand that this is an emergency only. The majority of the flight is done by computer because computers are just way better at squeezing out that last 1/10% of optimization out of a propellant budget that already only has 0.5% of margin in it.
Right, so most missions are probably planned that with that margin. And
Yep. And over the last 60 years, we have developed standards about what is a fair margin to carry into this. You know, the same way where we have rules about 45 minutes of endurance flying before you have to land. We have the same rules about propellant margins and propellant budgets, but it's not that big. It's not as big as we're used to thinking with propellant budgets in aircraft. We are talking a conventional mission budget has margins of a few percent, if that. The Apollo 11 landing with 30 seconds of fuel left, that's still characteristic of the amount of margin that we put into a typical mission, just because every kilogram is a killer. The nature of the rocket equation is such that every little bit of mass that you can shave out of your payload is going to save hundreds of kilograms of mass down the line on your launch vehicle. So we are strongly incentivized not to carry anything more than we absolutely need. Any other questions?
it's counterintuitive that changing the inclination takes as much energy as, because what I'm thinking is you just apply a delta V like ladder
You do.
across the surface.
You do, but it is
Is it because of the momentum, you're changing also your momentum vector, I would say?
So let's think about a spacecraft in an equatorial orbit and a spacecraft in a polar orbit. When they cross, when their orbits cross right here, think about their velocity vectors. One of them has a velocity of 7 kilometers per second due east, and one of them has a velocity of 7 kilometers per second due north. To go from an equatorial orbit to a polar orbit, you need to take your 7 kilometer per second velocity vector and change it to a 7 kilometer per second due north velocity vector. Think about how much energy it takes to take something that is going this way at 7 kilometers per second and turn it until it's going 7 kilometers per second opposite like that. It's a delta V of square root of 7 squared plus 7 squared, which is why it's so expensive. It turns out actually that the delta V required to take something from an equatorial orbit to a polar orbit is about the same delta V as was required to launch it in the first place. So taking something from stationary on the surface to an equatorial orbit, do that again, and you can take something from an equatorial orbit to a polar orbit. Yeah, which is why the ISS hasn't changed its inclination by even 1/10 of a degree since it was launched. It changes its altitude all the time, but not its inclination.
To what extent are the Russians still involved in all this?
Very involved. For no astrodynamics reason, but for programmatic reasons, the ISS was designed to make it pretty much impossible for any partner to leave on bad terms. The Russians have made a lot of bluster and noise about saying they're going to leave the ISS program. No one is assuming it's going to happen. It's not technologically possible for them to leave without the consent of the other partners, as it would be impossible for the Americans or the Europeans or the Japanese to back out without the consent of the other partners. If I was able to put money on the subject, I would bet an enormous amount of money that the Russians are going to stay with the program until the ISS is retired in 2030, no matter how bad the political situation gets. The program was designed to be immune to political squabblings, no matter how evil one of the partners gets.
Isn't the Soyuz the only boosting capable craft?
No, it was for a time, but currently we have that ability back now with the Cygnus, with the Northrop Grumman Cygnus vehicle.
Okay.
But most of the reboosting is still done by the Russian Soyuz, although when it's uncrewed, it's actually called a Progress, not a Soyuz.
So what sort of teeth did they put in the agreements then? Was this from countries just deciding to leave?
So the International Space Station is physically built so that the power and thermal comes from the U.S. segment, and the propulsion and guidance comes from the Russian segment. So one partner can no more leave than you can keep flying your plane without its engine or without its yoke.
It's still very impressive, though, that they were able to craft it in a way that so far has been kind of bulletproof.
Yep.
I mean, I'd be curious to read it. That's a diplomatic.
Yep. I mean, if you actually start listing through the steps of what would have to happen for the Russians to depart the Soyuz, you pretty much, to depart the ISS, you very quickly come to steps that require the participation of the other partners. They can't just close the hatch and press undock.
That's assuming the ISS still stays
That's what I-
viable.
That's what
Yes.
I'm thinking.
That-
When,
Which we-
when
which-
the Russians decide they don't give a rip
Shoot it
anymore,
down.
they're gone.
But that's just
They're
it. That's just it.
absolutely gone.
The Russians leaving would take down their segment
that-
as
yeah,
well.
yeah, exactly.
They would have to be willing to
That's my
abandon
point.
their segment as well.
That's where Plan B is, and you crash it
Uh-huh.
Statistically
Blow
speaking,
it up.
statistically
Nose,
speaking,
yeah.
that's probably the
Lots of
Pacific
principles.
Ocean. After the Pacific Ocean, it's probably the Atlantic Ocean. After the Atlantic Ocean, it's probably Russia.
I'm voting on the Kremlin, so
So
why mess around?
bringing the ISS down in a precise, controlled manner is actually a very large problem that NASA is not yet entirely clear on how to solve.
They should have figured that out in the
Um,
beginning.
Hello.
The beginning was the mid '90s. You know, this was very much a future problem. But the ISS partners have put out a request for proposal right now for, here are the requirements of a vehicle that can deorbit the ISS. Who would like to build this for us? It is a surprisingly difficult problem. It's not something the ISS can do on its own.
Yeah. It's so complex. You can't just, if you start deorbiting it as it's completed, the physics couldn't figure it out.
It will come back. It will come
It will
back.
come back.
But it could come back anywhere between 52 north and 52
No,
south.
that's the China way to do it.
Yeah,
It's-
which we're
it
not
comes
going
back.
to.
Where?
Yeah,
It comes
somewhere.
back.
But we're confident. We're confident that the ISS
Yeah.
components on
Yeah.
orbit, as is, can last through at least 2030.
Yeah.
NASA is not planning to start retirement operations until 2030, and if we're being realistic, there probably will be an extension
It
beyond.
hit somebody. We're talking about the Chinese one. It was like 2 years ago, right?
Tiangong.
They let it go. Right?
Yes, that was that was Tiangong
And
1.
they did this.
Yes,
Yeah.
the Chinese
Sorry.
default.
Yeah.
Yeah, the Chinese default position for upper stages is to not have an active deorbit mechanism. Under the international pressure, I suspect that will change in the upcoming years to decade. There is, even without an accident, they are rolling the dice every single time, and it is, it's not a good look if your nation crashes something on another nation. So the Chinese have just recently reached the primary assembly stage of their spacecraft, their space station, Tiangong.
The second one.
The second one, yes. There are three taiko-nauts on board right now. And I suspect in the near future they will cave to the international pressure of, it's the 21st century, stop crashing your rocket bodies at random points on Earth. But it's going to take time.
I'm still sort of smart. They don't have a plan for the space station. Never did, and we'll deal with it when we get there.
Yeah, we know what a vehicle has to be capable of doing in order to
Statistically,
be
it's gonna
orbited.
come down to it,
I,
right? So like,
Statistically.
Even bringing it down,
Statisticians.
even bringing it down in an ocean. Right now, if we completely passively deorbited the ISS, it's a 3 out of 4. It's coming down in the ocean. But 1 out of 4, it could come
One
down
out of
somewhere
four
on
is
Earth.
pretty high.
but in a large organization, everyone wants to do something cool and neat and exciting, and who wants to take on the lead of deorbiting the space station 30 years from now? They're going to be sitting in a little office in a corner and talking to no one. No, I want to do something else. You know.
I see it more as like, we do that all the time. I mean, look at the Hanford, like, nuclear thing. It's like, oh, we gotta build this.
Right.
Yeah.
Yes, that's true.
This
Okay.
is
Someday
something for
we'll
later,
figure it
whatever.
out.
Right.
But this is why we hope to build Orbital Reef and all the commercial LEO destination competitors, not just Blue Origin. That's why we're intending to build Orbital Reef, so we can transfer all the stuff that's on the ISS, all the experiments that don't want to be interrupted, we could transfer those services and distribute them to commercial space stations so NASA can feel free to deorbit the ISS. So all the partners can feel free to deorbit the
What did
ISS.
you call it, orbital reef?
Orbital Reef is the name of Blue Origin's
Yeah,
they
they-
proposed space station.
Okay.
But we're not the only one. Axiom had its own space station. NanoRax has Starlab. Northrop Grumman has basically a LEO version of Gateway. There's multiple commercial space stations being proposed to take over for the role that the ISS has filled excellently for the next 30 years. You're welcome.
I got another question for you. So are you saying then that if I've got, for a mission, right, it's effectively a collection of orbits, and then you basically have events where you transfer from one orbit to another.
Pretty much.
Why, so instead of running the engine sort of hard for a short period to change orbits, why not just distribute it and just have a lot lower thrust for a really long time and just effectively average it out? And is that even possible?
Because then you stop microgravity.
We can and do that. We don't do it on the ISS,
Right.
but any spacecraft, any satellite that's gone to GEO in the last 20 or 30 years has done something like that with a electric engine. So those types of engines are very low thrust. They're very high performance. They can do the same thing for 1/5 the propellant, but they have thrust measured in fractions of a newton. It's a very, very small thrust.
So it takes them a long time.
It
to
takes
make
them a long time. It's also suboptimal from a delta V perspective. The optimal way to do any of these maneuvers is get it all done as quickly as possible, what we call an impulsive maneuver. But because electrical engines can be so much more efficient, it can be like 5 times as efficient as a chemical engine in many cases. For example, raising a satellite's orbit from a geostationary transfer orbit up to geo orbit. The conventional way of doing that is by spreading it out over a month or so with a low thrust but high performance electric engine.
They're not good if you got people on board because they don't know.
It's never been done so far. No one has ever flown electric propulsion on a crew vehicle. Nothing against the laws of physics that prevents it. It's just never been deemed prudent because people want to get where they're going in days, not months.
But if you do that, then out of your numbers that you show,
Yep.
now they're all changing.
Now they're all changing. Talking about low thrust, high impulse trajectories is not something that we have the computational tools to do until like my lifetime. Because this approach, talking about the 6 orbital elements, is only valid as long as these assumptions hold true. And if you're constantly thrusting, then you have another perturbing force, and the law of universal gravitation is no longer applicable, meaning you can't talk about closed paths or Keplerian orbits.
Did you say it's less efficient?
It requires more delta V. It doesn't require more propellant, though, because the electrical engines are already 5 times more efficient than chemical engines. Okay. I think we need to make room for the parents' presentation that starts in 3 minutes. Thank you very much.
That was fantastic.